Greetings again. This is our fourth week video class and video coverage. Today we're going to talk about graphics and stack programming in CodeMill and finish it off with subroutine calls. During this fourth week, we learned about graphics capabilities of CodeMill and how we could actually write graphics programs in assembly language. And we could also do stack programming. So let me see if I can make a small correction. There we go. And here's an example of graphics programming in CodeMill. And what this does is it paints the perimeter of a 16 by 16 grid to red with a thickness of 2 by 2 cells. So to achieve this, what we do is we use what's called the setFrame command. So the setFrame command comes with two register arguments, as in this sort of format syntax we see, and a size specification, as well as a color specification. Now, I know that this 03 is the color code for red, and this is the size of the square that we want to, the side of the square that we want to draw, which is in this case 2 by 2 pixels. That's all it's saying. And so it is this sort of an instruction that we get to use to actually write this program. And so if you think about a grid for CodeMill to be square in shape, what we want to do is effectively paint this perimeter of the square, beginning on the left top left corner of the screen. Let me see if I can actually draw something to demonstrate it in a little bit. So here we have the square, let's say. So what we want to do is kind of do this effectively. Go this way. If I can make that visible. If I could get the thickness of the weights, okay. So maybe this will take me to a good place. Okay, now it didn't seem to work well. Let me try again. Maybe make it even thicker. So this is the thickness that I wanted, but it doesn't look like it is. Maybe just make this a little lighter in color. If I could just make it a little lighter, you could see, yeah, there it is. It's actually the same color that's why it didn't show. So we want to go this way first, and then we want to go this way the next step, like this way. After which we want to go the other way down here. So we want to switch this, we want to flip this. We want to go this way, and then finally we want to go this way. Let's flip that also. Okay, we actually want to rotate that. No, we want to just we want to flip it. That's all we want to do. Oh, that's not the one. Sorry about this. Let's see. We want to flip. There. No, vertically. I'm sorry. What did I do? There you go. So that's what we want to do with this program. We want to like draw pixels going from one side to the other, starting here on the left-hand side. That's what we want to do with this code. So naturally, what you want to do is you want to write some for loops, where these loops would simply traverse along these arrows. We're going to start here, place a pixel here, and then move, and then actually sort of like set the rest of the pixels in the same direction. Once we get done with this, and that is in and of itself a loop, because we're going to have to do this along the length of this grid, the screen, which is actually given to be 16, so we're going to have to set it to somewhere in that neighborhood. And the size of our square is actually 2 pixels on each side, so that means we have to stop at somewhere around 14. That's why you see that number here. And then we then turn direction here, turn south, let's say, and then we go in the same way this way, and then we turn left, and then we turn up. So effectively, this is what you really are seeing here. There is a counter for each of these directions, and the counter also keeps track of our movements in terms of like setting these pixels up. So we begin with this particular set of pixels, and for that we set our, I guess you can call it, column dimension to 0. So we're going to move along this, and as we do, we're going to change basically R0. And R0, as it changes, it will allow us to move in this direction. And then once we get done with this, this is basically what's happening here. This loop R is precisely what's happening here. We clear R1, then we set the first square of a 2 by 2, let's say square, and in colored red, and then we increment R0 twice. That's the x displacement. So we have delta x in this direction, delta y in this direction. So we're displacing, x by 2, I guess 2 pixels. And then we finish this when R0 gets to be 14. Once that is over, then we actually start going in this direction. And so now that we've reached the end of the first side of the grid, all we have to do is go down the other direction. So first we set the 2 by 2 square on this right hand corner, and then we increment R1 2 times. Now we're moving in this direction, and then we set keep doing this until in fact we get to 14. And then once we get down and finish with this, then we actually have to turn left, and as we do, we again set the pixel or the 2 by 2 square here, and then decrement R0 this time because we're moving in this direction. That means we're going to have to get closer and closer to the origin, and that's in steps of 2, and then we go back again to this place until we hit the point where we reach 0. And then after that we actually fix this. Okay, so that's just wanting me to get back on. Let me actually do this while we're at this, because I'm going to maybe demonstrate this. So let me just type my password, and then maybe we can get back there later. Okay, so so the last step would be just to go back up, and then for that we actually first reset the value of R0 to 0, because this would have actually taken it down to -2, and then we keep then painting these 2 by 2 squares here. And that's basically what this does. Now here's another example. This one actually doesn't keep it set. It just sets paints a black pixel at the top left corner again, and then it moves it along the perimeter, as opposed to like painting all the remaining pixels to mark the perimeter. This just moves this a black pixel once it actually sets it. So we don't want to use the set frame instruction here within these for loops where we actually make the move. Instead of like using SDF, we will end up using what's called a move frame instruction. And so what the move frame instruction does, it actually moves the frame that is situated at R0, R1, in this case of size 1, into that frame that is situated at R2, R1 coordinates, where again R1, R0 is the X, R1 is the Y displacement, and the same way R2 is the X, and then R1 is the Y displacement. So as you can see, we're actually incrementing R0 and then moving it into R2, and then moving frame-wise this frame that is sitting on R0, R1, of size 1 that is, into R2, R1. Since R2 has been incremented, a value of R0, this is what this instruction does, increment and move. This is just a move within the register here, R0 to R2. And that move then is followed by an actual frame move where a single pixel is moved, a black pixel that was set in at the very top left corner of our, let's say, grid screen. Now it's going to go into the next location. And then we keep doing this by actually moving R2 into R0, because that's what we want to keep, incrementing, and then going back to this place. Now that the next value of R2, that is, the next value of R0 really is in R2 as a consequence of this. Now we're going to get basically an incremented value of R2, and then we move again. And then we keep moving all the way until we get to the end of the first line. Okay? Again, if I were to really sort of like represent this by way of this example here, we're not drawing things anymore. We're just simply marking things. There's a black pixel, and maybe I could just do this by denoting this as a dotted line, if I can, maybe. So the thing is actually moving. Okay, it's no longer like staying permanently there. That is the difference here. We never see it in like as a continuum of lines, but rather we see it as like a dot moving along the way. That's precisely what we're doing here. Okay, and so now given that, all we're doing here is basically moving a pixel. This is why we use the move frame. In the earlier example, we only had set frame in all of these loops. You can see set frame, set frame, set frame, set frame. Now we have move frame. And the direction of the move is from here towards there. So for example, in the next loop, we're going to be changing not the first coordinate, not the delta x, but the delta y. You can see that's what's happening here. Now we actually increment and move R1 into R2, and then R2 all of a sudden becomes the second coordinate value. Here it was the first coordinate value. We actually updated from R0 to R2 is where we push things. Now we're going from R1 to R2. And so that completes the second loop. Now third and fourth loops are a little different because decrement instruction is what we use here, as opposed to like decrement and move, because there's no such instruction in CodeMill. All we have is decrement. So because of that, our first step would be to move R0 into R2 and then do the decrementation. So the two steps of this particular loop, now one step rather, of this particular loop has become two steps in here because we do not have a decrement and move. So we first move and then decrement. So this move and decrement is really equivalent to this step. And we do the same thing here in the last loop, which will be like this step going up this way. But besides that, the rest is pretty much the same. Again, this move is exactly the same as this move, and this last move is exactly the same as this move. So you can see what's happening here, that we have these move frame instructions that take care of our pixel moving. I'm going to try to explain these, demonstrate these, hopefully maybe even now. See if I can actually get that done. If I go to here, and let's see if I can actually log in and bring these in there. Now we log in there, and so we bring CodeMill up very quickly, and then I want to demonstrate this to you as quickly as I can. So the first one was we were actually drawing something. So I'm going to copy this stuff here and put it into CodeMill. There it is. So now all we have to do is just do this. Now I have to change the scratch pad size because this particular format of set frame works only with 8x8 or 8-bit register space. So this is exactly the rest of the settings will be. So I'm just going to push execute and see what happens. So this is what you get. Let me just actually do it again. So if I step, you can see what's going to happen. This is how the program is actually working in slow motion. And if I resume it, let me just come to the very end. You can actually watch the values of the registers over here. Nothing is moving in anything else except R0 so far. But now R1 is going to start changing, and then we resume to complete it. So that's what this does. Now the other program, this one down here, sorry, I got to get back to here, doesn't actually keep the pixels or the squares that we have. I guess this is the one that's a paint black one. So let me just copy this over to the same CodeMill application. You'll see this. So I'm just going to get a new window. Hopefully this also helps you learn how to program this and what kind of settings you may have. There it is. It's a little crowded there, but nevertheless, I'm going to erase this. I'm just going to execute. Now, if you can see what happens here, the pixel is going to move now. It's moving. So it's a move more so than actually like, setting all the pixels around the perimeter of the square or the grid. So if I just resume this, it may actually happen fairly quickly. You can kind of see that this is what's happening. So if I can suspend, I can always move it. And you can follow what is happening here. And again, I can resume. It's going to turn. And after a while, it may actually not look like it's rotated. It is rotating, but it is rotating. The pixel is going around this loop. So you now have that taken care of. All right, so that is what these two programs do. And now that we've done that, let me just briefly mention receive and send commands, and then the CHF instructions and CHF instruction. Basically, this receive is useful for using the keyboard, for example. That's one of 256 devices that CodeMill can interact with. That's the only one because this is how we set it up right now. But any other one of these input devices can actually be used to do lots of things with CodeMill. And then the send is just the opposite. CodeMill sends. Right now, the only device that, in fact, CodeMill can send information to would be the screen. So it can actually paint, for example, pixels with the send command. And these are devices, basically, both of them, in the case of receive and send, they're just device number one. Their IDs are both one. And then the CHF is the character frame instruction. So what I have here, we've done something similar to this in class. I don't know if it's the exact same program, but you can see here that we're clearing a frame of size 80. That means I'm actually setting myself a frame, 128 by 128 monitor, and then I clear two coordinates that are stored in R1 and R2. So that means I'm going to start at location, the top left corner of the screen, and then I go into a loop as long as I don't receive anything into R0. This is the receive instruction, which will receive things from the keyboard. That's what the 0 states. And R0 is where it's going to go. And then after that, I have a conditional jump instruction. And that instruction is basically going to keep pushing this back until we get to have something in R0 that's actually positive. So R0 is initialized when RC receive instruction is executed. It's initialized to a negative value, and therefore it's going to stay negative unless I type something on this keyboard that I'm like pressing on here or holding my hands over, and that will then change R0 to a positive value, and then this will not be true anymore, this condition, and then we'll just go through and then execute the next instruction, which is a basically character frame. All that is saying is whatever is read, the ASCII code is what gets in is then displayed in these coordinate values, and the color would be black. That's what I set it down to here. And then I change R1 by 5. So I move R1. It's the delta X displacement by 5 pixels to the right, and then I keep doing this until I get to be 122. Once I get done with that, I clear R1, and so make the displacement go back to the beginning of the screen on the left, and then I change R2 by 8, and then I keep doing this until R2 becomes 119. That's about the height of the pixel that we're going to need to stop at, because it ends at 127. And so then I keep jumping back so I can repeat this. Let me see if I can also copy this and then actually show you how this works. So this is a simple keyboard driver, we call it. And now we're going to do some small changes here. And I guess since I'm using only 4 registers, so that doesn't have to change, but I want to get the resolution up and reset it so that thing goes away. And now here the resolution is 128. So what I'm going to do, I'm going to basically execute this code, and then I'll see if I can type some letters. So here, execute. Oh, I'm actually still doing the old one. I haven't pasted this. Let me just bring the new program in. So now here we go. This is our simple program and keyboard driver. I reset, and I'm going to do now typing. My typing. Oops, what happened? It didn't actually execute. Let me see again. Okay, it did. I did not press the execute button here. Okay, so I had already typed these. Now I'm going this. And leave some space. You can actually even do return. And then do this. I think return is not programmed. It seems to me. It's something interesting. That should work out just fine. But so I type it, and as I type, and if I stop, it stops because nothing is coming in. So it's going to be in this loop here. And if I go continue, then I just type it. And now once I get to the end of this, as you'll see it now, I'm just going to change some, so maybe I can even capitalize this, and it's going to be all capitals. And then turn it. And then once I'm done with this, finishing all the rest of the screen, it's going to basically clear things up, and then it goes back to the top. So you see how this works. All right. And that's that program right there. And you would have it on this particular video. You could actually use it if you like. Now then this takes care of the input-output programming. The only thing that's really left for me to cover would be stack programming. So stack programming, this is the exact example that I gave in class. So we have these algebraic expressions, which we can actually traverse either in order, post-order, or pre-order. And in-order expressions require parentheses because we cannot deal with in-order expressions without parentheses. We'll have ambiguities. In this example, if I just don't put the parentheses around this, and if I actually end up, for example, adding B to C and then subtracting it from A, I'm going to get a wrong result. So I have to be using parentheses. So, but there are two traversals, two expression forms, which are known as post-order and pre-order, that completely avoid parentheses. So no ambiguities are contained in these expressions, even if you didn't use parentheses, and they're fairly attractive for stack type programs. Let me just go back. So in-order traversal basically says visit the left subtree, and then visit the root, and then visit the right subtree. Post-order is visit the left subtree, and then visit the right subtree, and then visit the root. Whereas the pre-order says visit the root, visit the left subtree, and then visit the right subtree. Now, what we're going to do with this algebraic expression, we're going to write a computer or a code move program to execute it. And for that, we're going to have the following convention. Code move stack has a ceiling as a floor. Also down here is a floor, and then up here it has a ceiling. In between, we have something called a stack pointer that keeps track of the top of the stack, and that is the top of the stack. So what happens is when you execute one of these instructions like add stack, the top two elements, that is stack SB and stack SB minus 1, they get added, and then the result gets put into SB minus 1 location, while we also decrement the stack pointer by 1. Subtraction is the same. What we actually end up subtracting instead of like adding, and we decrement stack pointer by 1. So the order of the subtraction is that the top element, bottom element gets subtracted from the top element. And this is kind of important for our handling of post-order and pre-order traversals. It so happens that pre-order traversal actually matches this ordering of subtraction. We'll just see this in just a second. And in post-order, we need to have what I call a duplicate stack instruction in order to, sorry, not duplicate, exchange stack instruction to be able to actually process this in an algebraically correct way. So now if we just go ahead and do these traversals, maybe just to see this, let me just bring this down up here. If I can just copy this over here. Go for this little copy, and then see if I can actually map it down here somewhere. I'll just keep it here. Okay, looks like it's in a good place. So I could show you exactly what these traversals do. Oops, the expressions I didn't copy. So let me go back here and then copy this also. And that should take care of it right there. It's going to go somewhere else. So I'm going to bring it right up here real quick. So now, let's save it also just in case. So basically, what in-order traversal does, it goes in like left, center, and then right. So we go left first when we start traversing from the root down. So left of the root is here, left of this root is this, and then the left of that root is A. And then we go to the root, which is minus, and then we go to the right, which is B. That's what this expression is, A minus B. Now that we've finished the left-hand side of this root, we go take the root, which is this plus, and then go to the left of this root, which is C, and then to the root, which is plus, and then plus D, which is this. And now that we've finished the left-hand side, we go to the root, which is actually this plus, go to the left of the right-hand side. Of course, we go to finish this root. We come down here, and then we actually go to the left. So it's going to be E minus F, I'm sorry, minus, and then F. And then now we finish that, it'll be another minus. And then we come down here, go left, plus H. This is what this expression is. If it's post-order traversal, we go left subtree, right subtree, and then root. So that means we come down here, and then we go to the left of that, and we go to the left of that. So it's going to be A, and then right, B, and then minus. So A, B, minus. Now we go to the right-hand side, left, right, and root, which is CD plus, CD plus. And then now we finish that, we put the second plus, which is that. Now that we finish this side, we go to the right-hand side, and we go to the left, and then we say EF minus, and then we go to the right of this, which is basically go to the left of that, GH plus, and then minus, and then plus. Pre-order says, root, left, and right. So we go to the root, we go to the root, we go to the root, so it's plus, plus, minus. We go left, and then we go right. Now that we finish this, we finish that, we go to the right. Of course, that's plus, and then we go to the left, and then we go to the right. Now that we finish all of this, we come down to the right, and then put a minus sign, and another minus sign, and then we put E and F. Now we go to the right-hand side, we put a plus, and then a G and H. That's the pre-order. This is also the program that does the Codeman program that actually handles this in as a stack program. So we just follow this pre-order. It says push H, push G, add the two together, which is this. Push F, push E, and then subtract. Now you see what happens is when I push F, F goes to the top of the stack, and then E goes to the top of the stack. It looks like I think I've done something slightly different. This is the right order. Then actually we would have gotten so root, push E, push F, I think is what I would have done in the pre-order. Okay, so there's something wrong here. You just notice it will actually have to be F and E. Let's see, I'm actually just a minute. This is the pre-order. Oh yeah, no, this is fine. I'm actually starting on the right-hand side. So I'm going in this direction. First I push F, and then I push E. Let's see, I think there's something missing here. Just a minute. It's supposed to be, since I'm actually pushing on the left, no, that seems to be correct. So then I think maybe what I said is not quite correct, just to say that the pre-order actually, so we must be subtracting the top element from the bottom one. That's how the subtraction works. I didn't quite write it that way. Because if I go back and do this traversal, when I get down to here, where the subtraction actually takes place, in fact, even here, we would have encountered that. But no, first we begin on the right-hand side. So let's just do this very quickly. So this is the first time I'm going to do a subtraction here. And I push E, and then I push, in a pre-order, I push actually the root. Now I mean, I actually, let's say, I push E and I push F after I actually put the E, the subtract operation, into place. So that's actually root, left, and right, which is exactly what our pre-order was. So with this, I think I could see that our subtract instruction here would not work exactly how I described it, because when I get to subtract this, what happens, let me see if I can draw this. What happens is this. If I can draw one of these shapes, let's see if I can get one of these shapes here. What I think is going to happen is when we push it in, fairly light, so that was this is the one I want to draw. Okay, so what really happens here is this. Let me see if I can quickly get a line here. Okay. So the way that we get this pushed in, it's going to work like this. Let's see if this is right there somewhere, the text. Right there, this box. So when I push, it looks like this is what's going to happen. I'm going to basically push E, push F rather, and then push E. So the top of the stack, so this is how it's going to work out. So this would be actually E here, going to go down to the top, and then we'll have F. And now when we do the subtraction here, oh, this is fine. This is fine. We get to subtract, actually, the expression itself is subtracting F from E. This is just fine. Everything's down here. So this is just fine because we push F and then we push E. Now E is at the top. And then, of course, the subtraction will just say E minus F. That's exactly what we wanted. That's what's happening. And so the same will take place as we get through this process. Having completed this, then we push, actually, we do another subtraction, which then takes E minus F. And then, and that gets to be subtracted from, that gets to be at the top of the stack. The GH actually would be still bottom here. So we would end up doing E minus F minus G plus H. Because before we would have gotten here, we would have also had down here this situation here. Here we would have had G plus H. That is a little bit like this. That's what we're going to have. So if we get E minus F over here, then we subtract here the second time, this subtraction here, the second one there, this one, and it will just give us, at the end of this whole process, of course, we're going to have here E minus F. Okay? And that will then just get this subtraction take place, the second one, E minus F minus G plus H, and then the whole process goes forward in this direction. Now we push C and D in this order, of course, and then we do the addition, and then we do a push and B, A and B, and then we do a subtraction, and then push. After that, we do two additions to conclude the computation. So this is what really happens with pre-order. Now here is something that I received from Jake. So I gratefully acknowledge his work, and he actually shows us what happened here, step-by-step fashion. And I guess this is for the post-order, not the pre-order. So pre-order is slightly different, and I guess I copied this from his program. I wonder if it also had the pre-order. Let me see if it actually, he probably has that too. No, he doesn't have that. I guess we did it for post-order. But pre-order would be pretty much the same, so I'm going to leave that. But here's at least the post-order. And then the post-order expression. Let's see if I can just copy Jake's expression here. This is the post order one, so let me see if I can actually copy it from here. Okay, so I just copied that. I'm going to also attach it, paste it in here, so you guys can actually, ladies, can take a look at this. Let's see if it actually copies. Yes, it did. This is his version of the post order expression. Let me just actually say that, but you can see that the exchange instruction comes into the picture. This is what I said you had to do. So this is the post order one. Post order, I guess, is what I have to say here somewhere. This one is post order there. And this one is pre-order. Okay, so you got this right there. Well, we certainly thank Jake for this, and then we continue. So now here is the next thing that I want to quickly cover. Subroutines are basically those things that are programs, assembly language programs typically, that can be called from another such program. Now in CodeMill, they're handled by using JSR, jump to subroutine, and RTS instructions. So I guess this is in CodeMill, not in every assembly code. It's just true for CodeMill only. And so I'd like to say that when a jump to subroutine instruction is executed, CodeMill saves the address of the next instruction in its stack and then loads the PC with the address of the first instruction in the subroutine program. Coming back, when an RTS instruction is executed, CodeMill recovers the return address from the top of the stack, because that's where it was stored, and reloads the PC with that address to resume the program from which the subroutine call was made. Just after that subroutine call, there's an instruction, and that's where CodeMill returns. So here's an example where we add the first 100 numbers using a subroutine call. So here's the register that we initialize to 1, and then we clear R1 where we're going to put our sum in, and then jump to a subroutine. So this is not a jump instruction, but it's a jump to a subroutine instruction, JSR. And then we halt. We come down over here, and we then say, jump if conditionally jump if R0 is greater than 100, and that says return to RTS. If not, add R0 to R1 and increment R0, and then go back to the jump. So when we finish with this, we return by way of a return from a subroutine instruction. So this is really what brings it back to here, at which time we execute the halt instruction and see the result, or just bring the program to a halt. And of course, by that time, we should see the results, whatever result that we're interested in. In this case, that's the sum that we want to see in register R1. Now here's the example we did, and you can actually see that the result of 5050 is what matured into R1, and that's what this program is. So actually, we could do this also by copying this program right here and executing it there. This is still possible because we're running this program. So let me just do new here, and then paste it in. It doesn't matter what we have on the screen. We're going to be watching this. So this is the program that I just copied. Let's see if I can just select this way. And I just want to make this a little bigger so you can actually see it more clearly. All right, so you see the code, and then what we're going to watch is this R1. See if it actually changes if I set it to decimal to 5050. Oops, what happened? Something happened because I didn't set the register size the right way. Let me actually change the scratch pad size to something that is, yeah, now it should work. So let's just run it again. 5050. So, of course, that is 100 times 101 divided by 2. That's by Gauss law. Gauss sum this is, and that's 5050. That is 100 times 101, which is what gives you half of that would be 5,050, because that number would be 110,100. All right, so this really brings us to the end of this particular video class. And what I think we'll do next time when I come back would be, so we covered graphics and stack programming and subroutines. But when we get back, we'll complete our coverage of CodeMill and begin microprogramming. That will be next week. Now, I briefly talked about recursive programs, but I didn't get to include it in here because I'm going to put that in our fifth week class and expand on that a little bit. So until next video class, take care, and of course I'll see you all on Monday, that is tomorrow.